Let me make sure over here. We'll find out what kind of state my slides are in today. It's always a surprise. Okay, so today is the 20th of February. We are on week 7 of CSE598, and Twitch is working. Fantastic. We are talking about primitives and memory mastery. That is kind of the next module or topic that we're going into. I last week said, hey, this is kind of like a boss module or think of it kind of like a midterm. And it is, but it isn't, right? It all depends on how well you write your code, right? Which is the emphasis on this primitives part, right? If we think about the things that we did in the kind of first half of the class up until this point, what did we do? We're not going to count speculative execution. We did printf, so we did format strings. What did we use format strings for? To generate an arbitrary read or an arbitrary write. We then did file struct exploits. What did we do with file struct exploits? Same thing. We said, hey, here's some other interesting system or series of functionality. How can we break this and use it to arbitrarily read or arbitrarily write? Then we moved on to heap. Okay, so then we did the intro to heap kind of Tcache stuff. What did we use Tcache to do? Arbitrarily read or arbitrarily write. Right? And hopefully, without it being like explicitly there, you came to this same realization, right? Where we're just using some piece and then we are writing something. And the question is, well, what can I really do when I have an arbitrary read and an arbitrary write? Well, we saw we can overwrite the table of functions, GOT. We can overwrite GOT entries, right? To turn that into arbitrary execution and how we can leverage those primitives to kind of do something more advanced. Is sound? Okay, that is muted. Good. Memes. So, one of the things which is definitely going to reoccur in this module is when you are doing these Tcache exploits, the order of the index that you malloc and free matter a ton, right? You should have probably felt this pain in the prior module where whatever you free last is at the head of the Tcache. And so you need to have kind of this mental model of what if I malloc 1, malloc 2, free 1, free 2, which index do I want to actually read? Which one is holding that metadata? Now you can reason about that with GDB, which is fantastic. But we're going to be doing quite a bit of this in this module as well, and kind of rapidly doing so. And as we saw with the last module, there's a lot of things to think about when you're dealing with the heap. Less so in the earlier levels, but then in the later half, we had safe linking, which all of a sudden kind of put handcuffs on what we can and cannot do, what addresses we can access, as well as what we can do. Did everyone get to safe linking? Yeah? Okay. This next module, everything has safe linking enabled, which means if you did not get to safe linking, it's time to learn how safe linking works. Because you cannot do challenge 1 without that now. Okay. Further memes about Tcache. So we said safe linking makes it so you have to have the address that is getting returned from malloc. It must end in a 0, and if it doesn't, you'll get to see this fine error here, which it sounds like many people had the pleasure of enjoying. Now, one of the kind of gotchas here getting this here is you don't necessarily know, is it that the address that I wanted was bad, or did I fail my kind of safe linking permutation, right? Because that check actually happens in the safe linking logic, right? It's after it gets decoded is the return pointer 0. And so if your safe linking logic is bad, you'll also see this error, but it may be because you are decoding the safe linked or protected pointer incorrectly. Hopefully that's not the case, because I think I explained how safe linking works in a nice write-up, right? I spent like a nice 45 minutes there, like erasing and rewriting my handwriting for you guys. Hopefully that was useful. Because office hours was like this, and that was great, but I don't know if it was as optimal as it could have been. So I'm hoping that write-up that I posted makes it a bit more clear as far as why this works instead of me just typing arbitrary things in an IPython terminal. Unrelated to the course, but I'm going to bring it up. Connor officially got his PhD in the past week here, so congratulations to him. If you are not familiar with Connor, Connor is kind of the origin story of pwn.college and what we see today. I highly recommend watching that stream. Okay, so the comment here from the class was claps for Connor. All right. Was that the defense stream is on our YouTube and Twitch as well. So if you want to check that out, you can to get some kind of background and great historical nuggets. People tend to like pwn.college, so good for Connor and good for us. All right, course schedule. We're still doing what we're doing here. We're in primitives of memory mastery. And then next week we will do advanced heap, which is everything beyond Tcache. Then we have spring break. Now I asked, I'll talk about this now. I think I have a slide to hit today anyways. I asked after office hours what people's thoughts were on spring break. My intention is that you have exactly what's written here, which means that you get spring break to be spring break, right? You don't have work assigned to you. The heap stuff is due on the 4th, which is the first day of spring break. And then nothing gets assigned until 3/8, which is just a weekend before we start, right? So you are getting a free week there. If you disagree and hey, I really want work, let me know. We can certainly figure that out for you if that is your desire. Grades. So how do we do with dynamic allocator misuse? Well, it's not as flat as file struct exploits, but as a whole, everyone did quite well, right? 50% or more of the class 100%ed it, and the quarter that did not 100% it still got, looks like, at least 90%. So reasonably good info there. That is not a meme. Grades are kind of a meme, but this slide is not a meme. This is reality. So we actually did better on heap 1 than we did in file structs, right? And so we are kind of seeing what we anticipated here, where the review was hard, right? Microarchitecture exploits was just brutal. Then we got into the land of, hey, these things are real. We can look at them in GDB. We can ask questions. This makes sense. And so that's good to see. Hopefully everyone feels that as well. As far as pacing, as far as progression here, people again are starting at this nice earlier point. This is, I imagine, Sunday, Monday, right? So as soon as they get done with the prior module, and we see a nice steady progression. So that's good to see. How am I up here? Okay. The class average right now is 92.94% as far as active students. Right there, I still haven't gone and checked if the roster has changed since last. Last week I said it was 91 point something, so we've actually improved as a class. That's a good sign there. Logistical things. Now I say here I'm going to leave spring break alone. That's the plan. I consider it an opportunity for you guys to take a look at speculative execution or any other modules that we didn't finish. You can still solve those challenges for 50% credit, which is not nothing. The second half of the course, I'm thinking about shifting around the topics a little bit. I still plan on covering topically all of the things that are here, but I may reorder them or condense some things. I will try and have a concrete answer for you as far as what the second half will be next week before spring break, so you have some idea of what we're getting into. In any case, it'll still all be new material, so you can't work ahead. It'll just be a surprise as far as if that is the exact pacing. There is something that I believe Jan announced just on here. It's not on here. I think he called it the quarterly quiz. So one of the things pwn.college is doing as a whole is we want to release new content kind of orthogonal to the classroom, right? We're just, hey, here's something cool that we want to publish and make available. I may or may not incorporate that into the class. The tough part there is Jan announced that it will be on April 1st. And so if we look at our schedule here, April 1st is not in a nice clean alignment here, which if I decide to do that, we may get a little bit of volatility on our schedule, right? But that's one of the things that I'm considering that may shake this up a bit. Okay. So I will give that to you next week. Spring break should be a break. Demo plans. So this module is called Primitives and Memory Mastery. We talked about the primitives part, right? We said, hey, all right, we can use format strings, that's primitive. We can use heap, it's primitive. We can use file structs, that's a primitive. Like how you generate or get that primitive is kind of a whatever. The other part of that is this memory mastery component. And that is if I can access one region of memory, can I turn that into another region of memory? So we're going to take a look at that. Now, this is the module, which I believe I hinted at, where Jeff is probably not the tool that you want to use. Instead, I'm going to highly encourage you to use pwn.debug. I am much less familiar with pwn.debug, but we'll take a quick look at why that is the case and how we can do some of the similar things that we already do in Jeff with pwn.debug. Question from Twitch. This is the one thing I managed to find in the 10 minutes of my 2 hours I had slated for prepping. The question on Twitch is, does pwn.debug have a scan equivalent? The answer is yes. And then, just as a reminder, safe linking makes a mad return, so get ready for that. Before I delve into this, which I'm just going to use level 1 of the dojo as kind of our testing ground here. I do not intend on solving it. I'm not even sure that I could, but we're going to use this as our example binary. Maybe. There we go. Does anyone have any question before we march our way here? Nothing?
Do we expect 365 to be anything this week?
Ooh, that is a good question. So I believe they are still on reverse engineering. Let's sneak a peek here and see when their due date is. Next Monday. So that is in perfect alignment with us. 6 days, 7 hours.
Yep.
We're doing
What's that?
we're doing race conditions. Again, would that be effective?
We are doing race conditions. Ironically, them slowing things down is good for you in this module because race conditions are easier to hit if the CPU is busy. But yeah, definitely be aware of that. There's plenty of students I'm aware of that are just like, I'm going to wait. And, we've told them, that things are going to catch fire not just in the last 3 hours or 10 hours, but probably a day or two before. If this does turn into a major breaking thing for us, we'll adapt, right? It's not your fault that they procrastinate. So we'll play that by ear. This is the module that is probably going to suffer the most from 365 procrastination. Good question, good call. All right, so not only does... No, what did I do? Not only does the dojo have Jeff installed, but there's also pwn.debug, which is an alternative plugin for GDB. As you see, my GDB init has things set for all sorts of things because people ask me questions and then I just kind of toggle around between them. However, the 3 things that are relevant here for using pwn.debug, this first one here, source opt pwn.debug gdb init.py, that will get pwn.debug installed opposed to Jeff. The second command is supposed to make it so that pwn.debug will do the thing that we want it to do. I'm not sure if this is going to work or not, but that's what the docs said. All right, and then this last thing here, you probably should have in your GDB init already. If you did 466 for the reverse engineering, when you are dealing with binaries that don't have symbols, this is a super handy value to have. Because if you copy that binary and it doesn't have symbols, this is the base address of the ELF. So then you can start referencing locations relatively when you disable randomness with GDB, right? And so that is something that is just handy to have in general. But the things that matter the most for this module are these 2 right here. What time is it? Cool. So if I run GDB on here, I get some amazing errors that I'm just going to ignore. And if I run this, it fails. Why did it fail? This is just me being dumb. Anyone? Any takers? Sudo. And this is not just the case for these challenges here, but many of our challenges, they try and access the flag early for some reason. And remember, GDB drops privileges. So I am in practice mode, so I can sudo GDB. And then if I run it, now it works. Okay, so all of these challenges follow the exact same pattern. And so what you'll find is one of two things as you're going through this module. Either you will solve like level 1 to like level 3 and be like, I got this, and do what this guy did. Be like, oh, it's the exact same thing. I just need to make like these small tweaks, and you'll just burn through the whole thing. I hope you do. Right? Alternatively, you may not, code your exploit nearly as smoothly, and there's going to be some pain as you repeatedly carve up your code. But they all work via this same mechanism, which you probably have seen before if you took CSE598, where this is a server, which we can connect to. And every time we connect, it is going to spin off. Could be a thread, could be a process. We don't necessarily know right now. Let's take a quick look. Okay. So we got our friendly welcome message. This is why it fails in this load secret guy, because that's going to rely on the flag. I don't want to go into pthread create. I want to go into every time that the main binary calls accept. Looks like it's going to Malik's argument. It's going to call this run thread. So this is a thread server. We look at run thread. Run thread is just a wrapper that fixes some buffering things, and then that calls this challenge function. All right, we've seen this kind of pattern before, and this challenge function is a infinite loop. It's going to interact. It doesn't give us a lot of instruction. If we look over here, that tells us just Malik free scanf printf, but we don't know like the arguments, right? If I go Malik, did that work? I don't know, right? These challenges have been around a little while, so they aren't necessarily built around quality UI. And so we have to kind of reason about this from the challenge. What does Malik want? Malik wants, it's going to call scanf, and it wants a number. What is that number? Well, that number is going to go into v4, and we see v4 here is an index into stored, which means we could reason that dword is some type of array. And then it is going to call Malik and mark stored. So it's going to track which indexes have been malloc. So it looks like it just wants one argument. It just wants the integer. Does anyone disagree with me there? Okay. So, 1, we malloc something. Malloc. 2, we malloc something else. Free is going to work very similar. Bam, bam, bam. Where is it? Free. It again is just looking for a number. That number is going to become a 0, or that number is used to access the stored array, which then will 0 it out. So this is just tracking what has been malloc and what has been freed, so that you can't like malloc, free, in theory. I don't know if it actually prevents that, but that is like a logical reason that you would want to do that, right? And then it's just going to call free on the pointer that is there. So we free 1, we free 2. Based upon the previous module, what have I done?
Created a deconstruct.
Maybe. Did we see how big the malloc was? But yeah, based on the previous module, you would assume I'm not doing anything super tricky to you here. And in the malloc case, we are mallocing hex 400, which I believe is the max size for a Tcache entry.
420 is the max.
Of course, you would know exactly what it is. But yes, it will go into the Tcache. Now, pwn.debug has different commands than Jeff. It is a different plugin. Is this large enough for everyone? Yes? Cool. Tcache bins is what I want. And when you type that, you're going to get this friendly message. And we need to read the friendly message, not immediately freak out and post on the Discord. Right? I would expect that from 365, maybe even 466. I would expect better from the people that are in this room. All right? If we read the message, what we see here is it says pwn.debug will try and resolve the heap symbols via heuristic. Does anyone know what the word heuristic means? Basically means we're going to try a bunch of stuff and like this is what we observe. It's a guess, right? Very sciencey word for like, yeah, all right, this looks right. And so pwn.debug is saying, hey, we don't know where the Tcache is, but we can like loop through memory and try and find something that looks like it. Do you want us to do that? And if we just say yes, then it says, hey, we still can't figure stuff out. Do you want a heuristic? You want to brute force this? Or you can just, yeah, man, just go for it. Okay, and now it says Tcache bin's empty. Well, Robert, pwn.debug was supposed to fix this. Why does this say empty?
On the challenge thread. The thread that's running the challenge, or the server.
Yeah. So this is a thread server. And what thread am I on? If I info threads here, we see that there are 3 threads. And the Tcache is a thread local cache. And so I'm looking at the Tcache for thread 1. And thread 1 is that thread server loop. It's just going to call accept and then spin off a thread. That's probably not what I want. So let's go to thread 2. Now it says switching to thread 2. Hopefully thread 2 is this one up here. Now if we run Tcache bins, we say pwn.debug make it happen, we now see the printout of the Tcache bins. Now it's a different display than Jeff, but can we reason about what we have here? And if I needed to like verify that this is the next pointer, 4 giant hex at this, except I want to go back by 1. This should look very similar, right? We said we're mallocing hex 400. This is our size. It's 415. Why hex 415? Why?
We're setting previous use bit, but then some other stuff.
So we're apparently setting other stuff. But the point is just the flags. I'm not going to dig into which flag. And the 10 is the hex 10 is because when we request hex 400, we malloc an extra 10 for the chunk metadata, right? And then the 5 is the flags value. So then this is our next pointer. Does this correspond to this guy? Kind of. What are you doing to me? What are you doing to me, pwn.debug?
You didn't automatically demangle it.
Oh, you're right. I'm looking at the mangle, right? Because safe linking is enabled. And so that all corresponds with our kind of reasoning here. Now, the thing that I wanted to, VMAP also works on pwn.debug. Just saying. All right. We said that we understand kind of what primitives are. And so we see the benefit of using pwn.debug for getting our Tcache info. Jeff currently does not do this. Like you will not be able to see the Tcache entries for these threads. So that is the reason I'm saying, hey, use pwn.debug. But VMAP also works on pwn debug. And when we talk about regions of memory, what am I talking about here? What is a region of memory? This is memory. But like the stack is a region of memory, right? The heap is a region of memory. libc is a region of memory. And what these challenges ask you to do, level 1 says, use an arbitrary read primitive to get to the BSS. Right? These are all, we hide a value somewhere in memory, and it's your job to go find it. And so level 1 is the BSS, level 2 is the threads heap, level 3 is a specific threads stack. And so these are different regions of memory. But you start off with the same thing, as was pointed out. You start off with, I can connect to this thing, I can malloc, I can free, I get this arbitrary read. So if I can arbitrarily read, well, like odds are, if I know about how Tcache works, what is the region of memory I'm most likely to leak immediately? A heap pointer, right? I could get a pointer to the heap. And so if we Tcache bins,
I like the mangled one though, right?
well, you could leak a mangled one, right?
You leak a mangled one.
Well, if you have a mangled one and you understand how safe linking works, well, or at least you have the magic function that does it, right? You don't have to understand it, but you can run the Python function that turns the mangled mess into a pointer. Then I could get something. Let's see, does this, I think this does. Does this have a, let's check it in IDA. Let's see if we can get a mangled boy. We get scanf, we get free, we get send flag.
Should have printf.
Does it have a printf? Okay, it has printf. So in theory here, we can say printf, which index do I want? 2. What happened?
Oh, we freed something, didn't we? So
We did free something.
There's no pointer to that region of memory anymore.
Are you sure?
Do we have the UAF?
What's that?
Do we have the UAF?
Do I have UAF? Right. Do I have a use after free? Right. And so if we, in the Tcache module, we were like nice about things for the most part, right? But this right here has that stored array is suddenly in our way. So when we call printf, it's going to check, hey, is this stored? If it is, right? If it's not, if it's been freed, we're just going to tell you none. So we don't give you that next pointer. This is where, in my announcement, race conditions exist, right? We can connect to this, and we can malloc and free, and we have to defeat this right here. There is a race, because there's a time of use, or time of check, time of use, right? Yes. I got to look at you, because like you get this face sometimes where you're like,
Yeah.
no, that's not right. And then it goes into my head.
Because I didn't use the race condition just to solve everything.
The intended solution relies on a race condition. There are other things that can be done, and it looks like I'll have to talk to you after class. But the intended solution utilizes a race condition such that you can get an arbitrary read, right? Because you now have multiple threads that are interacting with a common region of memory. So let's assume that I win that race. Then the value that I get would be this right here, which is that mangled guy that we talked about. Now, because we understand how safe linking works, we can turn this mangled value into a heap pointer, which would be thread 2 Tcache bins, which would give us this value right here. And so that gives me a location in the heap. Now I can use that to find the base of the heap. Does anyone know what the base is when we talk about that? Like we've talked about using base addresses for binaries. We want to think about regions of memory as contiguous blocks. And when I say contiguous, I mean they are right next to each other. So this starts at 3FE, ends at 3FF. Is that a contiguous block? Yes, that's why it's showing it to us. But does this contiguous block go further? Yes, because it turns out 3FF equals 3FF, right? And so we can just look here, keep marching our way down. And what we should come to realize is everything from here to here is one contiguous region of memory. What that means is if I get a leak, if I get a pointer in a running process that is in any of these regions, I can calculate a distance to any other pointer in this region. Now, the heap, is that contiguous with anything? No. But is this where that pointer is? Also no. So why does this say heap?
It's the heap of the main thread.
Correct. The comment was that is the heap of the main thread. And the heap of the location of that pointer is right here at 5A00. Is that contiguous with anything? Yes. It looks to be contiguous with this region right here. And so now all I get, the only thing I can calculate from that are these two regions, right? I can access any pointer that happens to be here. Now, the question that you started off with was, what is the equivalent of pwn.debug Jeff scan? And Jeff scan, everyone here know what Jeff scan is? Yeah? No. I don't want been true. I want capped. Okay. So scan is a Jeff command that lets us search a region of memory for another region of memory. And so I can do something like scan, and let's say, I don't know if this will be here, cat heap. Nothing. Let's try scan cat or scan libc. Not cool. So what I'm saying here is I want to scan for a pointer into a region of memory that is here. And I'm looking for a pointer in libc that points to the region that is capped. That was a lame sentence. Did that one land? It didn't land. Cool. So libc, when I say libc, it is filtering this VM map region down to that's the loader, to this region of memory right here, okay? So we're saying I want to look through all of memory right here, and what I'm looking for is any pointer that goes to anywhere up here. Why do I care about that? Because we are thinking about pivoting around in memory in contiguous blocks. So if I have a libc leak, right? But what I want is, for instance, in the BSS. Well, where's the BSS in memory? It's going to be somewhere in this contiguous block. All right? So if I get a leak of an address anywhere up here, there is some constant value that is the distance between my leak and some hyper-specific location in the BSS. And so what we are doing here, the pivoting part of this, right, the memory mastery, is, okay, I have a libc leak. Let's say I have a libc leak that is, I don't know, this right here, because it's the base. So I have this. Can I find a location that I can read a pointer into the binary? Yes. I would take the distance that I know, subtract the pointer location. What this is saying is at this location is this pointer, which points into the BSS. So if we like examine the giant hex, and I know how copy and paste works, right? At this address inside of libc is a pointer to the binary. Yes? Cool. And so if I want to get like the base of the BSS, right, or I want to get to that region of memory, and all I have is libc base, I can do the math where I take a location where I know there is an address into an address that points to the binary. I can subtract what I know, and if I print it, we get some constant value here. This is a universal truth every run. The distance from one point in libc to another point in libc is a fixed constant, right? And so my exploit then is to get the leak, calculate the distance, and then leak the new value. And so when I leak the new value, I now have an address that points into the binary. Now that I have an address that points into the binary, can I do the same thing to find the beginning of like the read-write section of the binary? Yes. I have this, and I want to find this. I don't know which is bigger. Well, that one was easy math. And so what we end up starting with is we have some heap pointer. Then we say, what can we find on the heap? I was using Jeff there. To circle back, P to P. Scanf is P to P. And so you can P to P heap libc. Let's see what we get. Nothing. Scanf. Let's do P to P. Yeah. Oh, no, I'm using scanf. P to P. There's got to be a pointer in like libc that points to libc, right? Like that seems reasonable. It's doing a lot of thinking. I just want to show that it works.
I know there's libc to stack exists.
Do you like libc to stack?
Yeah.
It looks like P2P is just, it's taking its sweet time.
You should try flipping because libc is too big.
You want to?
There's a pointer in the stack. Let's see.
Okay, all right.
Cool.
Well, we got there. We get a similar output, right? Where here is something that is, hopefully, we know how this command works. B8. Yes, that is on the stack, and that at this location on the stack is a libc address, right? But what we start off with is not a stack leak, right? The first thing that we could leak is the heap. And so what we really want to know is, well, where can I go from the heap? Can I go to libc from the heap? Nope. Can I go to the stack from the heap? Okay. Can I
put it in the heap? Will it check the thread arenas?
Probably not, because I imagine I haven't checked the implementation, right? Because what it is looking for is it's grepping these guys. So what was my actual leak here? Was it this guy?
Yeah.
Okay. So we would want to get for this magic string. We would P2P this page, and I'm looking for something on the stack. Nope. Can I get something in the binary? Nope. Can I get something in libc? Yes. Right? And so now that we're actually looking at the challenge, this might make a little bit more sense. We know that we can leak a heap address. Right? We can get that next pointer. And that next pointer is going to be in this region of memory. Now, based upon that leak, there's going to be some distance between this leak and a libc address. Interesting, and there are some kind of common pathways here. I'm kind of generalizing. What is this? Like, why are there libc pointers on the heap?
Because we're writing this stuff, and that uses the file structure too.
So, yes, it circles back to file struct, right? libc likes to have standard in, standard out, standard air implemented using file structs, and file structs are typically found on the heap. So that means that in general, you will find libc pointers on the heap. So then once I have this challenge asks for the PSS. So far, we can go from reading a heap address to reading a libc address. Then we have to apply that same logic. So now I know a libc address, so what do I want? P2P, libc to baby. Okay, so within the region of memory that is tagged as libc, we can find pointers that go into the binary. And then based upon that leak, we can calculate a fixed distance from the leak to the location that we are interested in memory. That is the pivoting component of this module. So this whole thing is, first, can you build up this fancy race condition thing that lets me get arbitrary reads? The second thing is, once I have these arbitrary reads, how do I reason about using them? Now, one thing that is particularly useful, at least it was last, is this little further reading guy. It's a blog post that talks about pivoting around memory. Specifically, why can we do this, right? So I said that the reason we can go from the heap to libc is because there frequently are file structs in memory. There are reasons for why you can dance from one location to another. And this blog post gives you some inspiration there. Now, one of the things that is a 100% gotcha for this module is ASLR is enabled. You're doing a race condition, and you are using scanf and printf. So there are a large number of fail states that you will encounter, not because you did anything wrong, but simply because you rolled the dice bad with ASLR. So what happens if this libc address that you need to leak, that's calculated dynamically, has a new line character in it? What's going to happen when you try and write that and then pass it in via scanf? You're going to have a bad time, right? Well, what's going to happen when the address you're trying to leak has a null byte in it, and then you call printf? It's not going to display, and you're going to have a bad time. There are a number of just poisonous, toxic bytes that simply will not work. And so you're going to write this exploit here that is that starts off with, okay, I can leak a heap address. And then as you start doing this dance from something that's in the thread heap to libc to the binary to the stack to somewhere else, any one of those could randomly have a garbage byte on this particular run. So your exploit should fail and fail fast, and hopefully not fail in a way that you have to hit enter again. Write some function that if you encounter this, right, I'm not getting, like if I'm doing a printf and I'm expecting, 6 bytes. If I get 4, just fail and try the whole thing again. Right? You're not brute forcing it, you're just waiting to not get hosed by ASLR. And that is this whole module. That is it. Right? Once you have written that primitive, it is just about repeatedly using it to dance around and read secret values hidden in different regions. It's not insanely complicated, but it requires you to write like solid exploits with reusable code. And then as you encounter problems, update your components such that you don't explode catastrophically. Does anyone have any questions about what was like rambled about there?
Yes.
Yes.
If your program fails because of like ASLR randomization, would you have to like just restart the program to rebuild the device?
Yes. So like my suggestion, and I will write something that does this during office hours. I've learned at this point that it just doesn't make sense for me to live code in this 1 hour time frame. And it's just too tight, where office hours is way more fun for that because we can stumble our way and I feel like I have to check the clock a lot less. But what you should do is have some func, and let's say what does this do? This will be like call printf, right? And this is going to call printf into that binary, and it's going to return some results. And so I end up with something like this. I would immediately, like, if the length of what I'm getting doesn't equal whatever I'm expecting, then I would just raise some exception, right? Or return false, or whatever it is that you need to do, and build that into your logic. Right? So this throws up an exception, and then up at your topmost level of your program, you just abort and then run again.
Restart the server, like
restart the server, like kill the current one, abandon chip, we're bad roll of the dice, let's try again. Now, as a consequence of that being the case, you need to be a lot more strategic in how you're writing your exploit, because you have to when you use GDB, you have to be like, okay, why did I fail, right? Did I fail because of bad bytes? Did I fail because I'm thinking about it wrong, right? Because this exploit will fail, even the intended, right? Like I want to say in our verify script, we say up to like 1,000 runs. Right? Realistically, you don't need to run it 1,000 times, and it's quick enough to where like this isn't a time-consuming thing. A well-written exploit will still find the flag within 30 seconds. Okay, so this isn't I need to brute force this overnight, right? I'm going to run this script and go to bed. If you're doing that, there's something else wrong with your logic, right? But you can write totally valid logic and still fail simply because of ASLR. Does that answer your question? Cool. Like I want to say what I did in a demo last year was exactly that, where I just raised an exception and then I caught it at the topmost level, killed it, and then restarted. So that was just in a loop, where it was just, if we threw this exception because something didn't behave as we anticipated. We just short-circuited my loop and jumped to the top. And then if we successfully got the flag, we broke out of the loop. All right, Twitch is quiet. That's okay. I'll blame me. Class time is just less entertaining. I don't know what to say. I've got 7 minutes. Anything else, guys? Because that is essentially what I wanted to communicate. Because like writing the primitive here that gets you, that does this race, is going to be your first hurdle, and that may take you a couple days. But once you have that, it's totally reusable in every single level. And so I don't want to do that right now, because then it's like, hey, here's like half of every challenge in this module.
Quick question.
Yeah.
So something is, you mentioned at the beginning of the class, the unaligned error. You said it could happen also if your address is aligned. So if your last.
Oh yeah.
What was the other reason? Because I think I'm running into that error.
Okay, so that is, which I doubt it is what you are running into. What did we call our magic scanf function? Wait, we had a name for it. I don't remember what it is. I was going for consistency. All right, but demangle.
Oh.
Yeah, that's the word that I want. Like, guys, like I really like I exist in a superposition of time and space. Okay, so we wrote some type of magic demangle thing, right? And it looked something like this. And what we said was, see if I remember this right. Don't copy this for the record. This is probably wrong because I have to think about it too, right? You write it. Mid is going to equal pointer bit shifted by 12, and then we said return mid XORed with mid bit shifted by 24, like something like this, right? I don't know that this is correct. This is why I write stuff down and reuse code. If your logic here is bad, then you could also encounter that, right? Now, why would that happen? Well, if we go back to office hours from Friday, and then that write-up that I did on paper, in particular, the paper write-up, is what was the assumption about this like one-off demangle function? Do not copy this, sir. that just took in the pointer. There was an implicit assumption that allowed this to work. Do you remember what it was?
At first, like some bytes, they have to be the same.
So the implicit assumption was that do I not have? I don't. Gosh, dang it. The pointer and the location of the pointer are on the same page. You're nodding, but do you understand why?
Because like when you do the shifting, then you're kind of checking. You're assuming that they have to cancel out or something.
Right. So what's really happening, if we go back and look at the mangle function, right, which is what happens in that, I think we can get to reasonably quick. If we go back to the misuse, we link to libc. And it is this protect pointer function. This right here, right? This is what we're trying to reverse. And yeah, there's some numbers here. But it actually takes two arguments, a position and a pointer. When we have that one-off demangler guy, we are assuming that pointer bit shifted by 12 is the same thing as position bit shifted by 12. And for small allocations, it is, because these are small allocations that are on the same page. But if we start malloking and then freeing large things and small things, and like this program has been running for a while, this like assumption is false. And so instead, what we end up doing is we write a demangle function that takes a pointer and then some offset or some distance, right? And when we do that, we do what it was that I wrote on the Discord there, where I showed how if the position and pointer have a distance of 1, where you need to do that addition. Or if it has a distance of 12, you would do that exact same logic. And I provided the actual Python function there, right? And so if your logic here is wrong, you can also encounter that Tcache unaligned error because you are decoding the value incorrectly, right? Or you are writing a bad mangled value such that when it does get decoded, it doesn't decode to what you think it is, right? Because like essentially what we are doing, like if I wanted to, in my arbitrary read, I want to overwrite the next pointer, right? To be a pointer to libc. So I have some logic that's going to be like mangle libc pointer, and then I'm going to say write next pointer. This is obviously garbage pseudocode, right? But I have something like this, where I'm trying to write to the next pointer a mangled version of a libc pointer. What is the relation between this libc pointer and the position? The position that I'm trying to like put it in. Because remember, the actual logic that I'm trying to reverse is pointer and position. The pointer that I'm trying to write is this libc thing. But what is the position?
It's like wherever in Tcache it's stored.
Right. It's going to be that heap leak. So that heap leak that we know, when we get a heap leak, hopefully, not necessarily, and in later challenges, absolutely not. But the early assumption that you can make is the heap leak that I get for the next pointer has some relation to this position, right? Because when I malloc free, we said these allocations are hex 400, right? So that means that malloc free would be on the same page, correct? Well, hex 400 plus hex 400 is hex 800, which is less than hex 1000. Right? It should be on the same page unless there's a whole bunch of stuff going on beforehand. So that means I could take my heap leak and bit shift it by 12, and it should be equivalent to this right here, because my leak is on the same page as the location that I'm writing. Now, if I did like malloc, I'd have to do it 5 times. That 5th pointer would not be on the same page.
So you have to adjust the opposite.
Right. I would have to account for that information as far as, okay, well, the leak I got is for the next page. So the position address is going to be my leak bit shifted by 12 minus 1. But what if the page is 12 pages, the leak I give is 12 pages later or 20 pages later? Well, I can figure that out. The behavior of the heap is deterministic. So you can sit there in GDB, malloc free. Okay, who cares, right? As long as it's a repeatable series of actions, when you observe the kind of state of the program, you can still deterministically say, if I leak the nth thing, I can infer a constant distance to some other thing that I'm interested in. In this case, the thing that I'm interested in is the page that I am trying to overwrite the next pointer. Does that?
Yeah, it makes sense.
Cool. And like that is intended to be a problem that you run into in this module, right, where that assumption works early on and then that assumption breaks. And if you are encountering that, you have to figure out, well, is the problem in my logic? Is the problem in how I'm doing the mangling, demangling? right? And the way to figure that out is to examine the addresses in GDB, right? And reason about what exactly you're seeing to verify your assumptions. It's an excellent question, though. Cool. With that, I believe you guys filled the time for me, so I will leave it there. If you have questions, hit us on the Discord. Goodbye and